In the present lecture, we will discuss the example problem on tensile test. Let's see the problem. In a tensile test on a specimen of mild steel, 12.5 mm diameter and gauge length of 200 mm, the following results were recorded. So it is the load versus the extension. So load is in the Newton, extension is in mm. Then determine the value of Young's modulus of elasticity, and also they given the when the specimen was afterwards tested to destruction, the maximum load recorded was 58,500 newtons. Diameter of neck was 7.35 mm and the length between the gauge mark was 268.7 mm. Then determine the ultimate tensile strength, percentage of elongation. So let's see the solution. So first to write down the given data. So here it is given the initial diameter of the specimen or original diameter of the specimen. Let's consider the D0 equal to the 12.5 mm diameter. Then cross sectional area will become the original area or initial area. Let's consider A0. So A0 equal to pi by 4 D0 square. It is the pi by 4 into 12.5 square. So then original area A0 becomes the 122.718 mm square. And also they given the gauge length or original length or initial length. Let's consider that is the L0 equal to the 200 mm. And also next given the data, load versus the extension. Then we have to determine the Young's modulus of elasticity. And also they given the specimen was afterwards tested to destruction. Maximum load recorded. So maximum load equal to the 58,500 newtons. And diameter of neck, it is given the 7.35 mm. So after the test, diameter at the neck is the 7.35 mm. So final diameter of the specimen is, that is the diameter at neck. Let's consider the DF equal to the, it is given 7.35 mm. Then area of the neck AF equal to the pi by 4 DF square. So it is the pi by 4 into 7.35 square, and so area, final area equal to the 42.429 mm square. And also given the final length of the specimen after the test, let's consider that is the LF equal to the 268.7 mm. So then we have to determine the ultimate tensile strength, percentage of elongation. So here we have to determine the Young's modulus, ultimate tensile strength and percentage of elongation. So let's see the calculations. So this is the given data. So first we have to determine the Young's modulus of elasticity, E value. So for this one, before that we have to draw a graph between the load versus extension. Load in the vertical axis and each unit is the 5 kilonewton load, and extension is in the horizontal axis and each unit equal to the 0.05 mm extension. So next to draw a graph for the different loads respected extension values. So this is the graph for the load versus extension. So then we have to calculate the Young's modulus of elasticity, E value. So we know the deformation formula, delta equal to PL by AE. So from this equation we can be write as Young's modulus E equal to PL by AE. So here P is the applied load, that is the tensile load, and L is the initial length, and A is the cross sectional area, and delta is the extension. But here we know the initial length L we know and initial cross section area we know, but P divided by A we don't know. So P also we don't know and A also, delta also we don't know. Then this equation we can be written as L by A into P by delta. So that is the capital A equal to L by A into slope of the graph. So this also have to remember. So one of the formula. Sometimes we can be determined with the help of the graph by using this formula. So Young's modulus E equal to L by A into slope of the graph. So for the slope of the graph, observe the graph and here up to 35 kilonewton graph is linearly varying. So up to 35 kilonewton and 0.282 mm extension point. This point we are calling as the proportionality limit point. Then slope of the graph will become the load, that is the 35 kilonewton divided by extension is the 0.282 mm. So E equal to L by A into 35 kilonewton divided by 0.282 mm. So L also we know and cross sectional area also we know. Then substitute L value, initial length that is the 200 and the original area, initial area is the 122.718. So here we know L and A and P and delta. Then substitutes all the values in the E equation, we will get the Young's modulus value is the 2.03 into 10 to the power. So this is the 10 to the power of 5 Newton per mm square. Okay, next we have to calculate the ultimate tensile strength and percentage of elongation. So we know that ultimate tensile strength equal to ultimate or maximum load divided by original area of cross section. So in the data it is given the maximum load and also given the initial or original area of cross section. Then substitute this all. Maximum load is given 58,500 newtons and initial cross section area of the specimen is 122.718 mm square. Then ultimate tensile strength will become the 476.7 Newton per mm square. Okay, so next we have to determine the percentage of elongation. So we know the percentage of elongation formula. So that is the final length minus initial length divided by initial length into 100. So percentage of elongation equal to LF minus LI divided by LI. Here final length equal to 268.7, initial length equal to the 200. Then substitute this LF and LI value. Then percentage of elongation will become the 34.35%. And also we can be determine the percentage of reduction. We already discussed percentage of reduction formula is the initial area minus final area into initial area minus final area divided by initial area into 100. So initial area, so A naught or AI, whatever you have to consider, AI minus AF final area divided by AI into 100. We know the original or initial area 122.718 and also in the data given that one the final area, so AF equal to the 42.429. Then substitute AI and AF values in the percentage of reduction equation. We get the percentage of reduction. So this is the percentage of reduction. So percentage of reduction equal to 65.43%. So this is the solution and thank you.